So thanks for coming to the DCG Tech Insights. Usually this is packed full of a lot of material about what Intel's doing in the data center space, but we chose to actually take a slightly different perspective today and bring some people on that are going to talk about how data centers run and what's happening with this hyper-evolution of technology. So today we have John Wilkes from Google, Scott Carlson from PayPal, and I'm Kamhaut from Intel. So what we're going to do is just a quick trip down the memory lane, view across the current known. We'll have John come up and talk about what they're doing inside of Google. Scott will speak about what's happening inside PayPal and then where we're going. So, I always like to, think about a history of where computers are, and all of us probably have our personal history. Mine started with an Apple, probably in 5th grade. Where a couple of us were allowed to program it and do cool stuff like Logo and Basic, and I assume some of you probably tried this stuff. And some people, were probably, using an Atari instead. This was actually my real first system that led me to like computers and with the gaming. But if we step way back in time, the talk here is about abacus to autonomics. If you think about the abacus, this is really kind of the first computer, a human touched it. Operating it wasn't really that hard. You had one-to-one, and it helped you, figure out your math problems, and it actually lived for a really, really long time as a core. In fact, you can still use one today if you really want to. And if we jump just a little bit forward into the future, this is the ENIAC, which is like 1940s. This is the first real computer, and this is an interesting one that kind of talks about the problem that we're having today. It had something like 18,000 tubes. It had like 500 flops. It could actually do some math faster than people, but with those 18,000 tubes, if just 2 of them would die, basically the whole thing would go down. So actually it only spent about half of its time actually online. So they weren't really thinking about design for failure, but it was fairly effective to get things started. Was anybody an ENIAC user? No ENIAC operators? Okay, good. So, if we just jump forward real quick into, what's going on today, just want to give some kind of perspective. If you think about the brain, it's 100 billion neurons. There's been some people, you can't really say flops to a brain because, brain's analog and computers are digital. But Kurzweil says, maybe it's 20 quadrillion flops, so 20,000 teraflops with 100 billion neurons. SETI at home, if you're familiar with this, it's a distributed system, 3.5 million nodes with 681 teraflops. The most recent Intel platform, the CPU, the Xeon E5 V3, if you take 1 million of those together, and like on Monday we had Microsoft talk, and they stated that they're over 1 million servers now. But if you can imagine all those running 500,000 teraflops, we basically have a couple brains, right? So we're getting to the point where we're really pushing the evolution of technology forward. Diane talked earlier, if you saw her, and this is just a common thing that we're seeing, with things like the devices, Internet of Things, wearables, edge. This is pushing what's required in regards to computing power on the back end, as well as what's on the front end. And it's a constant cycle that we're seeing as we make resources available, the demand increase. There's actually I think it's the JVOX concept where you basically, as you expose more capacity, easier to use, people are going to consume more, and they're going to find new innovative ways to do this, and it's a continuous cycle. As we go down this path, there's many, many challenges. So we're basically in 50% reduction in compute costs every 2 years, thanks to Moore's Law. The data volume is growing drastically. And basically, we have to, as we're doing this, we can't just continue to do the things the same way. We have to decrease operational costs with increasing scale and consistent performance. So a basic topic that we're talking about, just take it to a very simplistic perspective. You can almost see a data center future operations like a brain, where it watches like a human does, looking at telemetry and sensors. It collects this information. Then you can have analytics that make decisions on what's going to happen, and then it takes actions. So if you look, like an application developer will watch their app level, infrastructure guys are watching the server storage level, but we believe you can bring this all together with sophisticated analytics and start really driving a concept that looks like how a brain operates. And as you go through this flow, it continually learns. So as it finds a takes an action and gets a good result, it knows about that. If it takes an action and gets a bad result, it knows about that. Just like we, in our daily lives, have this happen to us. So just want to give you the background, and I'm going to ask John to come on up and give us a perspective from Google. So John, thanks for coming.
Good morning, everybody. So we put up a new data center every few months. This is a picture of the inside of one of them. Happens to be in Lithia Springs. And we don't add any people to our operations staff when we do that. Why would you? It's just software running on more machines. So how do we make that possible? Well, the first thing you need to be able to do is be able to build things like this machine here, this data center, at scale. I'm not going to tell you how many machines are inside it. You can count if you're quick. The second thing you need to be able to do is to cope with what happens when a system like this says, I am desperately running out of free space. I only have a few petabytes of storage left. And the third thing you need to do is you need to worry about what happens when things break. And it turns out that things breaking dominates the behavior that the operations staff take when they're dealing with systems like this. Performance we can always add. We just throw more machines at it. We buy more stuff from Intel and other people. But making things work when things are falling apart around the seams turns out to be the single hardest thing we have to worry about. So do things break? All the time. It isn't worth spending a huge amount of energy putting redundancy into every single component that you have available when you've just got lots of them lying around. But what that means is when you get to this kind of scale, and it's reasonable to think about 10,000 machines as a unit of management inside one of these data centers, you're seeing about a few failures per month, or possibly per year, per machine. So it's quite normal if you're running, say, a 2,000 machine service. Think like one instance of Google Calendar. We've got a few copies scattered across the globe, but one of them will have maybe 2,000 machines it's touching. That's going to see 10 machine failures a day. And the trick is to consider that normal, not a special case. Just look at this setup here. This is actually inside the same place. There's a bunch of cables, and you can imagine what would happen if somebody were to accidentally brush against those cables. You could imagine, there are people running up and down the aisles fixing things. There are, at the top of the racks, there are top-of-rack switches. They provide connectivity to order of magnitude 80 machines underneath them. That is basically a single point of failure for that set of 80 machines. If that switch breaks, everything underneath it goes away. So you need to worry about how do you place stuff to make sure that all of your copies aren't underneath one of those top-of-rack switches. The thing, remember, is dominated by failure. There are some very big, thick copper bus bars about the size of my hand going across those things. Each one of those copper bus bars powers about 2,000 machines. They're passive. They don't break often. When they do break, it's spectacular. But you can lose 2,000 machines at a time. You could lose quite a lot more than that if you lose a 2 megawatt PMDC and maybe its diesel generator doesn't kick in time in order to be able for the battery backup to work right. So you have to worry about what happens when all of the machines, 2 megawatts worth of machines, disappear simultaneously. You also have to worry when people like drunken hunters shoot at the network connectivity that's up in posts in various parts of the state because, they're drunken hunters. And that takes out an entire site. And when you lose a few terabits per second of networking, even we notice. So one of the things that you get to worry about is you worry about the scale of individual applications sitting inside a data center like this, sitting inside the machines. You worry about what happens when this data center itself suffers partial failures, and you worry about when entire data centers become not available to the rest of the universe. Once you've worried about those things, you can start asking questions like, how do we make the system more efficient? But first, you've got to get it right. Then you can worry about efficiency. This here just happens to be a graph I picked off of some recent experimental work we're doing about packing virtual machines onto physical machines. Each vertical line here represents one physical machine. The top, I think, is CPU, and the bottom is memory. And we're trying to, each different line color represents a different virtual machine with a different combination of CPU and memory allocated to it. And we're trying to pack these as efficiently as possible. White space is bad. We took a look at this graph and went, that sucks. So we're actually working on making this better. We have some of my colleagues are busy, furiously trying to improve this stuff, because every piece of white space you leave lying around in this kind of context is stuff that we could have sold to one of you, thereby maybe reducing your costs if we could sell more of them. Most virtual machines, and including the ones from us, come relatively fixed sizes, right? You get this many cores plus this much RAM, and there's, you've got a product line to pick from. We have a dozen or so. Our competitors have like 40 to 50 of these things. But you get to pick a particular set of sizes that you want to do. That's not how we do things internally. What we let our developers do is they say, I want this much memory, and I want this much CPU, and I want this much disk traffic, and I want this much disk space, and they just say how much of each they want. In fact, most of the time they say, you choose for me. Why would you have developers spending time on doing this? This is an example of a control system. People turn out to be really bad estimators for how many resources their computing systems are going to need, especially if you tell them, if you underestimate, we'll kill your task. What do? You guesstimate what it would take, and you double it. So that leads to waste. Waste is inefficiency. Inefficiency is money. Money, we'd rather have it for other purposes than sitting around idle. So what we bring to the equation here from our own stuff is not only having to cope with packing VMs, which are relatively nice and sort of granular objects into these things, but also completely arbitrary sets of workload. This graph here happens to be from a trace I published back in 2011, which captured every single job request, every single task placement decision, and 5-minute data about every consumption of resources across CPU and memory and disk, I think. For a medium-sized data center for us, it was 12,500 machines for the entire month of May 2011. It's available on the web. You can find it. Knock yourselves out. See if you can do a better job of placing stuff than we did. This here just shows you some examples of how long things run for. And there's two sets of lines here. The solid lines are batch jobs. You are happy if they exit, because it means they finished. The other thing is what we call service jobs. They run things like Gmail and Google Docs and back-end storage servers and stuff like that. You are unhappy if they finish because it means they crashed. And what we'll do is we'll restart them. So now you talk about what the lifetimes of the two things. So it turns out that the majority of batch jobs are short. And thanks to folk like the suppliers in this room, they're getting shorter. Batch jobs are doing more stuff in more parallel in less time. So the average lifetime of a batch job is shrinking down towards tens of seconds. The median lifetime. The service jobs, however, basically run forever. You'll notice that this is a cumulative distribution function, that the right-hand axis, it doesn't go to the top. That's because some of these tasks ran longer than the lifetime of the trace, which was 29 days. This is normal for us. It's a perfectly reasonable thing to want to be able to keep it up for months at a time. That system, I should have mentioned this, came from an analysis we did for a scheduling system called Omega. Omega is a replacement for the previous cluster management system that shall not be named. So Omega is the new one. I don't have time to talk about the details of the architecture here, but let me show you one of the things that motivated our switch towards it. We're in the process of rolling it out right now. So when you're trying to schedule the stuff like we saw just before, things that run for a few tens of seconds and things that run for months, you probably want to make different algorithm choices, right? For things that run for seconds, you put it wherever it'll go. It doesn't matter if you make a mistake, it'll go away soon. Things that run for months, you might actually think about things like, can I do careful Monte Carlo simulations to maximize the availability in the face of all the kinds of failures that we were talking about earlier? Yes, it's worth spending a bit of time because it's going to live there for 6 months. You don't mind waiting a minute to get the thing scheduled because you only do this once every third blue moon. So in our previous system, our monolithic system, both of those things ran in the same place. They were sort of, you finished one thing and then you started the next one. There was some prioritization, but first order, imagine run to completion for each of those scheduling things. So the stuff that was cheap and cheerful got stuck behind the ones that were expensive to place. Result, unhappy people who are sitting, where is my patch job? Why hasn't it finished yet? So this here is a graph of what happens to essentially how busy is the scheduler. That's the vertical axis against, it doesn't really matter the details, but as you make the jobs harder to schedule along sort of the two axes towards the back. So at the front is things that are really cheap, at the back things that are really expensive. And two things to know. First is up is bad because it means the scheduler is busy. It doesn't have time to be working on stuff that you care about. And the second is red is very bad because it means that it didn't manage to place that job in time. You waited too long and we gave up. Now, there's a simulation study, but it was fed by data from real traces. So that was sort of what the monolithic scheduler did. At the time, our competition was a thing called Mesos, which was from UC Berkeley and Twitter. It's now actually available as an open source product. I would strongly recommend it if you're trying to set something up as a great place to go to look for examples of how to build these kind of scheduling systems. There are others out there. That's the one I happen to know best. But they were our academic competition. So we included them in the study. In fact, we had one of the interns work on this who was a student from UC Berkeley. This is how Mesos does. So the first thing to know is, great, down is good. So it spends less time. It has some parallelism inside, which is wonderful. The thing that's not so good is it's all red. We know why, they know why, it's on their list of things to fix, but it has to do with the order in which you do things. Basically, you end up giving something to one and other things time out. Not good, but the underlying ideas behind Mesos are absolutely wonderful, and I'm completely supportive of it. I wouldn't be showing you this if Omega didn't do better. It's down, which is good, and it's all blue. Great. So these are the kind of things that we do to try and understand whether when we're going to make a change, is it going to help? Right? So we try very hard not to experiment on the live system unless we have to. So this is an example of kind of workload simulation studies that we were doing. And then we rolled it out on a canary cell, and then we tried it out for a while, and then we rolled it out to other things. So again, when you start thinking about keeping things up, you worry about what happens if it doesn't work well. So there are two tasks of a software developer in this universe. The first is prove that your brilliant idea helps. And the second is prove your brilliant idea does no harm. The first is easy. The second is where you spend most of your time. And this is what the result looks like. So there are two sets of graphs here. The x-axis is time in days. This is from that trace we talked about earlier. And the vertical axis is how full are the machines. Now, let's focus on the one on the right for the moment, which is how many resources have we allocated to work that showed up. The stuff that is in pink are serving tasks. We don't ever want them to lack resources. If somebody shows up with a web request, we want to serve it. We want to serve it quickly. We don't want to have to wait. We don't have to page anything in. So we basically almost pin resources for those things. But the stuff like the batch task, you know, if they have to wait around for a few seconds, they'll pick it up later, no big deal. So the green and the black represent resources that are allocated to lower priority batch tasks. We distinctly distinguish between the stuff that matters because it serves ads and the stuff that is batch tasks that could be delayed. This is a business choice. What it lets us do, though, is to overcommit the resources. You'll see the allocation is above 100%. That is intentional. I'm not going to go into details of how we do it, but this is a conscious choice we get by effectively increasing the utilization of these machines. Despite that, the thing on the left-hand side says there's still plenty of room for growth. We're not actually using most of those resources. In particular, the ratio between the pink stuff on the left, which is the consumption, and the pink stuff on the right, which is the allocation, is, you know, large-ish. It turns out that's deliberate. When Michael Jackson died, the spike in web traffic was large enough that we thought it was a denial of service attack. The best thing to do with them, by the way, is just serve them, because then the bad guys don't know that you know. If Michael Jackson dies again, we need to have capacity to be able to serve it. So that's why we consciously have headroom, and that headroom is what we're able to use to run other stuff inside. Most of the time, it doesn't need to be exercised. Okay, like other people, we put multiple tasks on one machine, multiple different kinds of jobs. So we'll run batch tasks and front-end serving tasks on the same physical hardware. One of the things we wished our hardware suppliers did, hint, is to provide more concrete performance isolation between the multiple tasks that are competing for the same physical resources. The kernel scheduler does a pretty good job about allocating CPU threads and the like, but it turns out that when you start worrying about the classic example is an intern who doesn't know any better, writes a MapReduce job that trashes an L3 cache. That has unfortunate side effects on the things that was trying to serve out of that same machine. And as you can see from this graph here, we're a touch thread happy. I think this is the way things are going to be in the future. As we go more and more towards supporting mobile stuff, asynchronous, interactive response is going to be the way of the future. Everything that used to be single thread is going to have to be replaced by stuff that is much more responsive. So what do you end up doing? What we found ourselves doing is saying, how can we cope with this interference that takes place? We don't have hardware support, so let's do it in software. If you're running a big job, though, you've got, like, say, this I think was about 400 examples of 400 different tasks of the same job running on the same kind of hardware, doing the same work. Right? We've got load balancers at the front, splattering work across all of them, so they should be behaving the same. We measured their CPI, cycles per instruction. Note, they are not all the same. In particular, the people on the right-hand side are suffering badly. They're seeing slowdowns of 2 to 3x compared to the median. That gives you a control signal. You can now do something about it. We can actually take those ones on the right and either rescue them. There are two ways of rescuing them. You can say, I'm sorry, you're in a bad place, let me kill you. Because we're going to restart you somewhere else. Remember, failures are normal. So the way we do migrations internally is we kill an original and we start up a new copy. Or you can say, I've looked around all the other things running on that node and I think that one is a problem. Let me do something bad to it. If it's a batch job in particular, we might just say, there, throttle it. More details in that paper. You're welcome to go look. There's lots more interesting information that goes there. I didn't mention this, and I should have done earlier, that we use containers, C groups, for our isolation between all of those tasks that are running on those machines. Most of the stuff that we do doesn't run inside a virtual machine. The exception is the things that we support from the outside. It's a great security barrier. Containers themselves are not adequate, but virtual machines we use. We use virtual machines based on top of KVM. Those processes that run the VMs themselves run a container. So basically everything that runs inside Google runs in a container. Fun fact, we launch a couple billion of these things a week. So we have a little bit of practice. What I want to do next is to try and give you some ideas about what we think a model based around containers can bring you that the traditional model of sort of putting everything into a VM doesn't bring. So I'm going to switch gears in a moment and talk now about sort of some open source stuff that we're pushing out based on our experience in these areas that we built up over the last decade or so. So containers are really good. We're really excited to see Docker come along because Docker does a very nice packaging of a set of technologies that makes it really easy to pick something up and put it inside a little wrapper and then run it wherever you like. None of those technologies is particularly new, but the combination of them is really tasteful and really effective. So we've jumped onto the Docker bandwagon and we've said, great, well, it's nice to have one container, but we're looking at scale, right? We're looking at what happens when you get more than one container. Well, you need to start orchestrating the control and management to bring up off them. So the system we've produced and we put out an open source version of this is called Kubernetes, which is Greek for pilot or helmsman or steersman of a ship. And it's an open source system rather than a closed one. We're giving this away because we want to give people the idea of here's the way we think is a good way to structure your large-scale applications because we want people to do more of them in the hope that then they will come and buy stuff from us or to run them on. So the first versions of Kubernetes we pushed out run on bare metal hardware or on Google Compute Engine. Since then, other people have come along. I think I just saw an announcement from Amazon saying there is a version that runs on AWS. Azure is on board. There's a bunch of other people, Rackspace, and we're working hard with people like Red Hat and CoreOS. So it's Docker, right? It runs everywhere, which is wonderful. But what do you do with it? So here's the way we think about it. Suppose you have a trivial example of a web server, and web servers are complicated beasts. They're doing very fancy stuff, but they are generating a clickstream. And that clickstream might, let's say, for the purpose of discussion, represent money. You never want to lose that clickstream. So what you do is you write a little separate thing that takes the clickstream that is coming out of the web server and very carefully writes it out to persistent, secure storage somewhere else. If the web server, being this large, hairy, complicated thing, falls over or has a bug, no big deal. The log roller captures that clickstream and is able to push it out, so you don't lose any money because your web server had a glitch. Those two things need to go together. There's no point in having the web server over here and the log roller over there. You want them to be joined at the hip. If you look at traditional ways of doing things, you'd stick that inside a VM, and then you'd have to build up an operating system, and then you'd have to make sure you did the antivirus patches, and then you'd have to make, et cetera, right? Why is your developer spending time on that? They want to be able to just package a web server and a log roller together and get on with life. So that's basically the unit. We wrap these things around in a container themselves. In fact, we took each of those things in a container and we put the union inside another container, and we call that other container a pod. So a pod is the unit of scheduling. We place pods onto machines, and everything inside a pod stays together. It lives together, it dies together. And because we're doing the placement onto the machines, Kubernetes does this for you, and because it's Docker, you really don't care where you end up. Whether it's that machine or this machine, it doesn't matter. You shouldn't be caring anyway. You should just be caring, does your web server do the right thing? So the Kubernetes master, which is you can think of as the control system for this, makes placement choices, picks a machine, puts it there. Great, so you've got one pod placed. Some little while later, you've got a few more pods. How do you keep track of all of these things? So this is the second technology we're encouraging people to pick up and use, and so far it looks like it's going quite well. We've introduced this notion of a label. A label is just a key-value pair supplied by the user, and you can set the key to anything you like and the value to anything you like. There's some limits on how many you can have to stop somebody using a key-value store, but the idea is they're user-oriented labels you slap on things. And I've shown here, I've just colored, or I've just attached a label saying back-end or front-end to each of my pods. There's a mixture of them. I've got a lot of them now. This way, I can now start talking about tell me about all the things that match this label. So we call that a label selector. And you can talk about the group of things that match. You don't have to list them. You don't have to name them. You don't have to know what they are ahead of time. You don't care which ones are in the group or which ones are out. They're just in the group or they're not. And you can do things like, hey, let's upgrade all the front-end web servers and leave the back-end ones alone. Just by saying, here's a label selector. Do this operation on things that match this label selector. You can have multiple labels. You can say, you know what, I'm going to separate the canary stuff from the production stuff. And I only want to do a test on the canary versions. Or I want to see what is the performance I'm getting from the RPC latencies or the HTML serving latencies for the production front-end things. These are all just label selectors. So the idea is this applies to monitoring, it applies to configuration, it applies to control systems, and it applies to scale. So scale, how many web servers do you have? How many front ends do you have? How do you need? Well, the way we'd like to do it is we introduce a new idea here called the Replica controller. It's not actually it's not rocket science. It's just a thing that says, I have this template, and I want to make this many of them. And it does the following. It says, how many of them do I have? It runs a label selector query, compares that with the number it's told to get. If the number is different, it fixes it. It creates them or deletes them. Remember, they're all the same. It doesn't matter. That's all the Replica controller does. It's a little building block. One of the other ideas in Kubernetes is this notion of microservices that you can compose. So if you want a replica server that's doing this thing, you just add that. The other idea is this notion of a desired state. As opposed to saying add one replica, which is a command you give, you say make the number of replicas equal to 3. Do what you have to. That is so much more resilient to things happening, to ordering considerations and stuff like that. Maybe there are bring up rules that you have to have, but the process of getting to 3 should be observing those bring-up rules rather than you hardwiring those bring-up rules into a script that causes you to get from 3 to 4, because tomorrow it's going to be 30 to 37. So we've gone from 3 to 4. Great, so now you've got a pile of replicas, but you don't want to have all of your clients know that how many replicas you've got and where they are. So what do? You put a layer of indirection in the front. All known computer science problems can be solved with a layer of indirection. We call that a service. Whatever. It's basically, think of it as a load balancer. Right? It provides an IP address to the outside world, and it does dynamic load balancing of work across the back ends. How does it find its back ends? It uses a label selector. You get the idea. There's a few simple ideas here that keep on getting reused. So, quick summary for Kubernetes, and then we need to move on to other stuff. So pods are the way you group containers together, so you get sort of co-location and common fate. Labels are the way you identify things. Label selectors let you talk about groups of labels. By the way, of course, labels sets can overlap. Think Venn diagrams. You can have any arbitrary combination. You get to choose the labels. Replica controller does what it says, and services are a way of getting indirection and give you a chance to do load balancing across a number of backends, and you can hide those details from your customers. If you want to join, it's an open source community. We are actively developing in the open. I submitted a pull request recently, actually just got accepted for what we call the resource model. How big is a pod? How do you write down how big a pod is? So you work out how many of them you can pack into a machine. Great, so that's now out there. You can actually look at that and see whether you like it or not. If you don't like it, send me email, send me comments. Kubernetes is, you'll notice, it has this nice blue logo thingy with 7 sides on it, unlike all of our other nice blue logo thingies which have 6 sides on it, because those are our internal products. Kubernetes is the open source one that doesn't quite fit. That was intentional. I do like working with people who are this smart. We view it as just a complement to the stuff that we're trying to provide behind the scenes, right? We would love you to build stuff on top of Kubernetes, because then that gives you freedom from a particular underlying cloud provider. We would love you to then run your Kubernetes systems on top of Google Compute Platform, because it gives you all of these other nice services and performance and productivity and stuff like that. But, you know, you should be looking around for what the best place is. And then finally, just a thought to end on. Kubernetes is still, actually, to be honest, like most of the other open source stuff that's out there, is at the stage of this bicycle here, right? It's a wonderful thing. It's really helpful, but we've got a ways to go before we get to the sophistication of the kind of systems that we've seen behind the scenes earlier. We will get there, I think, in the open source community. One of the reasons for doing this is to have more people participating and making that happen. But in the meantime, look forward to taking advantage of what you can get and helping make it closer to and more capable like the stuff in the back. Thanks.
Thanks, John. Thanks. So now we're going to have Scott come up. Scott works in PayPal. I met him a number of years ago, and he shares quite a bit about what they're doing inside of the data center. So Scott, tell us about how you guys are doing automation and components.
Hey guys, so I think it's important that at the PayPal side we talk about why we would do something like this more than the how, because the how for PayPal is very similar to how a lot of people are doing it. We've talked about in the past, big VMware shop, big OpenStack shop. We're starting to use a lot of these industry-leading technologies to do this. But one thing that's different about us is because we grew so fast as a payment provider, we have to think about how we can do this very securely, very safely, based on sort of bank-ready engines. So when we take a look at how we need to scale inside my data center, I have to consider what my developers want to do to release things like a new mobile app that takes payments, or I want to take into account something that I want to do internationally. Global is interesting to us because I would suggest, unlike Google, we have so many local regulations on how we can store payment data that we can't just spread everything all over the place. There's a lot of localization that goes into where we put people's data, so we can't just scale everything all over the place all the time. It's interesting about PayPal is if you look around some of our history, we were mostly physical until 2011, early into 2012, because that was the only way that we could guarantee performance and spec and all those kind of things against our compute platform. We have a lot of C++, it's compiled, and we pretty much scale by how much spec int our app takes. And so what we had to do is we had to figure out, let's take all this Intel hardware that we have, let's figure out, I give my workload a whole compute. How many do I need to service my holiday capacity this year? How many do I need? How many spec do I need to go across the world to service this customer base and this product across this application? What's sort of interesting about how we scale this, and we're starting to do this on OpenStack, we're one of the sort of leading sort of OpenStack enterprises out there on the payment space, is we had to look at all of our sort of core enterprise applications. PayPal was built on top of big Oracle and big IBM, just kind of like a lot of the bank people. But how do we take that and how do we turn it into a cloud? How do we turn it into something that's consumable? How do we scale something that required a database at one point that housed really important customer information that is protected by all these security controls? How do we actually scale it into a cloud without breaking it? And that's really interesting, not really just from a technology perspective, but also from a human perspective. Human beings, when they're used to, I've said this before, come from an enterprise shop. They're used to deploying another Oracle database. They're used to deploying, rack, and let's add another node to my rack cluster. They're not particularly used to scaling 4,000 machines at a time or 8,000 machines at a time and making everything disposable. It takes a lot to train your developers to make their thing disposable. They have to forget about state. They have to forget about all these things. And when you're fully encrypted, fully SSL all the way through, there's some interesting challenges for that. Standard things that what matters to PayPal. Let's reduce the cost. Let's go to the cloud. Let's make it all consumable. We heard a few minutes ago about how it's interesting to stack virtual machines inside of containers and inside of KVM, and we're fighting with that today. One of the things that we look at recurringly through our payment stack is how we solve the noisy neighbor problem. We have a lot of apps that are big C++, they're compiled, and they have a significant number of I/O purely because we made some decisions around not retaining things in memory. So we have to create and destroy instances very quickly, purely to eliminate some risks in that area. And so when you do that, the I/O gets high, and if you put something with it where there's no, where it also needs I/O, you start to slow things down when you shouldn't. So inside of PayPal, we used to start thinking, like we'll say February, for how much capacity am I going to need in November this year? PayPal, as you can imagine, eBay, all other sort of shopping places, we have a Black Friday problem, and we have a Christmas problem, and we have a shipping problem. People in the United States like to buy everything on Black Friday and Cyber Monday. And surprisingly enough, one of our biggest days is the last free shipping day before Christmas. And so when we take a look at, let's forecast the 200% growth for this year on what we need to scale that to, it used to mean let's double the size of our data center this year. Where are we going to find that space? How much more dense are we going to make our hyperscale compute? How many more CPUs? Do we need to switch generations of CPU? We had to think about this stuff in February so that we could bring in hundreds of racks and scale that up and potentially switch virtualization platforms just because of the scale gets different every year. That took weeks, months, years. And now we're at the point, we're in 2014 now, where we can scale most of our stuff in minutes at the front end. And it's interesting that we've been able to get there. Autoscale is challenging for us. One of the things that we are constantly fighting with, and a question that you have to ask when you get into can the data center really think for itself, is does your system have to scale all together all the way through the stack? And so in our case, we'll call it a 3-tier architecture, right? Frontier with lots of different web servers that do a lot of different things for a lot of different products. And we have a lot of mid-tier services that take care of our big fraud engine and our big risk engine and our big payment engine and more different credit card flows and international footprints. And all these things call all the other things, and all of them talk to HSMs, and then they all talk to the databases. And so if you all of a sudden add 2,000 servers to your web tier, is your database big enough to handle that? Because you can't really scale an IBM P-Series box with a compute engine. You can't really scale an Oracle database up by adding infinite number of rack engines. And so when you take a look at an enterprise sort of environment like PayPal, you have to auto-scale it like this, but there's parts of it that you have to humanly scale along the way to be ready. In Google's case, I would guess they have to build a data center before they can build VMs in the data center. That has a big planning cycle ahead of it. They have to kind of know how many data centers I need ahead of time. I don't know how long it takes them to build a data center, but it's probably more than a few minutes or a few weeks. So you can't scale it unless you're ready. And in our case, ready means, do I still have the power? Did I bring in enough racks? Is my database big enough? Did I add the right kind of flash tier? Do I have enough HSMs? Am I right internationally? Because then I can auto-scale the stuff that's disposable. We do have the kill it, rebuild it philosophy. I've talked a lot about in the OpenStack world, the cattles and the puppies thing, right? I don't know if everybody's heard of the cattle and the puppy nomiker, but in a lot of enterprise shops, you have a lot of puppies, things you bring into your family and you take care of it and you feed it special and give it a lot of TLC and you want it to live with you for your entire lifetime and it is so special to you. You want your puppy to live. But cattle, on the other hand, you kind of just consider them disposable, right? If it gets sick, you take care of it, or if you turn them into meat, whatever you do with cattle, right? They're disposable in many ways. They're not like a puppy. You have lots and lots and lots of them, and they scale forever, and when you are done with it, it just goes away. And we're trying to get to that point in all of our front-end infrastructures because people don't need to spend time going to troubleshoot something that you have 4,000 of. They really don't. 10,000 of, right? There's no reason a human being should ever log into something, except maybe the first time, to fix it if you can just rebuild it. And that's really hard for a lot of sort of basic knock people who are used to getting, here's an alert, let me go log into it, let me restart Apache. All right, that's kind of silly when you're dealing with scale because it makes a lot more sense to know what your couple of use cases are. Apache goes away, just rebuild the whole thing. You get an error in the log, send that somewhere, just rebuild the whole thing. The disk goes bad, get rid of it, build it somewhere else, right? Pretty much all the problems in disposable compute can be solved by just build another one. And the human being side of that is really interesting because it doesn't feel right as a sysadmin. I know sysadmins like to write a lot of scripts to go do things, but they still kind of get a little bit uneasy with the whole kill it and it goes away. They like to go see programs work, but they don't rebuild their system all the time. And so what's sort of important for us is these 5 checkmark areas. Instrumentation is really important. if you come from an enterprise shop like ours, one of the things that's often missing is the instrumentation that's inside of your compiled application. There's a lot of cool things in the cloud now, a lot of cool things in public that you can watch the memory, watch the CPU, watch the threads, all that kind of stuff. That's not really trivial when you're talking about millions and millions and millions of lines of C that you have to compile every release. How do you put a memory hook in there that logs the right thing so you can actually react to an out-of-memory condition outside of watching the operating system? So instrumentation is something that you really need to look at because you have to sort of make the decision. In our case, we've started to decide to go to Node.js. We've got a big open source thing out there on Kraken.js. It was our contribution to the Node community. And so we've started to say, let's stop trying to fix all this legacy stuff. Let's put it on Node because we know it's safe and secure. We can scale it, and we can start to do these things that we've wanted to do before. Definitions and state machines of action, that I'm calling them, are really interesting. Hardware comes along with it because it needs to exist anyway. But you have to be really good about deciding what your action is ahead of time, because that way humans don't need to get involved. Just like a lot of different projects, a lot of different reactions, you have to decide under what circumstances am I going to allow the computer to take action here. And then you test it, right? Test, test, test. In many cases, you have to do some of this stuff in production. You have to put it in front of the users because it's really hard to simulate a 1,000% traffic increase on Black Friday or Cyber Monday. It's really impossible to simulate Michael Jackson dying. You kind of have to do it in a small scale, but you have to sort of put it in a test, and then hopefully it scales infinitely in many cases, or at least until you run out of real hardware. And what I like to think is, humans need to be able to get involved to handle the not expected and the scary things. Sometimes you need that smart, availability expert, data center expert, site access to get in there and be like, I have never seen this before. What new thing do I need to write? What thing do I need to study? What pattern do I need to build? There's no reason humans should ever handle things that are, oh, I know what to do. Because you can build that into a machine that they can respond with and deal with it. Hold on. Come on. So one of the things that you have to think about is the can we and should we here. Can we? Absolutely. A lot of this stuff is at the point where it all has an API. It all has hardware. You can auto-build it all. You can auto-tear it down. You can do all these things. Are you ready for that? All of these cool new advances by Amazon and Google and Intel, everybody, right? They're all ready for you to take advantage of. But you have to think about the ramifications because you do not want to break your business doing this. The big one, there's really two that I've had experience in my career doing this at big companies, is the cascading failure, right? If you can't build something fast enough, but you start to auto-take things down when there's errors, all of a sudden you have things like, let's say I do round-robin scheduling, right? Or I do least busy. So one node breaks, so I take it out. So hey, guess what? All the connections go to the next one. All of a sudden that one breaks. And then you take out your whole load balancer worth of nodes because things just go from one another, and then they break along the way. And until you see that, until you go, oh, you really don't know that you could just take out your whole data center purely by doing the right thing by taking out a broken node. The other one, to me and to PayPal, is I think scaling up is really easy, right? In many cases, disposable compute, you can build more and more and more and more and more until you run out of hardware. That's pretty easy to just build something, stick it in a load balancer, put a certificate on it, and hey, look, it's taking traffic. Taking that away when you're done with the holiday or done with the event is a little bit more scary, especially in our space, because we have to consider, is their data still there? Is there a transaction still in flight? I have to let that payment go through. I have to always give my customer paying with PayPal 100% guarantee that their payment goes through the minute they click submit. Because the last thing we want to do is have them think they paid for something, have them think they took the money away, but the money actually didn't go away because we killed it somewhere in flight. So scale down is really interesting as I take a look at my stack to figure out what is going to happen when I scale this up. Yep, we're good up here. It's kind of scary down here. But then what happens when I scale it down? Do I have to bleed the traffic off, et cetera? And in our place, I consider eBay and PayPal. PayPal is part of eBay. I think everybody knows that. We are one of the biggest Fortune 500 startups that I've been at. We're a huge engineering shop, always on the edge of all sorts of different things. But we are really an engineering payment company at PayPal, right? We're a bank in some countries. And so we can't just go do all these crazy things without considering we need to be the most secure payment company in the world. We need to take actions that are appropriate locally. And the humans, need to get in the way of this autonomics and letting the data center think. We do a lot of work. Our data center people, under D. Nelson, he's spoke at a lot of conferences. Our data centers themselves take a lot of actions. We have some really deep industry-leading hyperscale compute. We run 50 kilowatt racks in some cases, and we try to put as much compute density in a rack as we can. Our data center itself thinks a lot. Our compute nodes, they can rebuild themselves, and our VMs can get created. The human side of that has to get involved. You have to think through all the use cases, and you have to make sure that this automation is the right thing for you. All of the people like Intel and Google and whatnot in the open source will help us get all the point to where humans can decide, do I turn this on automatically, or do I have it just alert and take action? And that's what's important to us. And that's it. Das, why don't you take it from here?
Thanks, Scott. All right, so I got some cool perspective, and I'm kind of an IT geek. The thing to note is that not everybody's doing this type of thing. So I asked John and Scott to come, basically to articulate what people are doing on the future edge. We do want everybody to move to a software-defined infrastructure. We believe this has to change at scale across the entire industry. The technology trend is leading us there. We do believe that we have to drive to a lower TCO. We do have Moore's Law. Moore's Law has been able to drive down the cost of the system while increasing the capacity. And we believe that all data centers across the world should be dropping down to Moore's Law through orchestration and through software-defined infrastructure. It's not just about cost. As you saw, it's about agility and reliability. My last job in enterprise IT in Intel, we had a concept, hey, everybody should be able to have an idea and have that as a production service in less than a day. We're in a fast range of evolution, hyper-evolution in technology, and so we use some technology like reusable services, expose everything as APIs, utilize containers to make this happen. Other shops can do this too. The second is on uptime. It's very common inside of normal enterprises to have downtime. Downtime should not exist. We don't expect it, and we don't see it with our consumer apps that we utilize, and it's starting to become more normal to know that everything should just basically always be on. I want access to all my apps and data, anytime, anywhere, in any place. So we chose to build a self-remediation framework similar to what you see with what PayPal and Google are doing. We watch things with tools like Nagios and other capabilities that we have internally. We take actions with tools like Puppet. And we use services on top of things like OpenStack and Cloud Foundry. So just to remind you again, we really want to see this transformation and software developers to get involved to help us go through this flow of watching, deciding, collecting, acting, and learning. The data center and the software that runs inside this can basically move down this path. From a watcher perspective, and it's all about increasing perspective. You look at the top of the iceberg, you can look at the app services and the data that the operating system exposes you to today. But if you actually go underneath and look underneath the surface, there's dragons there, but there's also a lot of gold. So I like that John brought up L3 cache. Because there's actually something that we're bringing forward into the open source community first, where you can actually look deep into our silicon, very low level, and actually go after a very key element that causes contention, which is in the cache space. So with Intel Xeon E5, E3, we can actually pinpoint what thread is actually chewing up all the cache and hogging it. And this is a hard thing to actually really find very easily today with a lot of Linux performance tools, but we're bringing this forward first to the open source community, and I expect we'll start seeing it through many orchestration solutions. A second piece is, as we're growing these giant data centers, power is becoming an increasingly large cost if you look at the total TCO of the environment. So something we also care about quite a bit is how do you expose the powers and thermals and utilization. So recently we've, through either IPMI, which is a pretty standard methodology to access servers, you can now get in and start looking at very detailed information at the thermal level at each node. As well, you can start looking at detailed utilization information out of band, as well as you can utilize it in band. So we have some open source code that you can go ahead and use. It's called Node Manager. It's a firmware that basically sits on the platform, and you can utilize this to take a node-level perspective of what's happening with thermals, utilization, and power. And this is important as you start scaling your data center. You may be able to pack everything, to 100+%, but there will be some situations where you'll make a choice that you should move that system either to a lower sleep state or maybe, turn off whole chunks depending on what your business model is. So our goal is to deliver this telemetry to these systems of orchestration so that people can build, amazing applications. A third thing I want to leave you with is a thing that we're driving towards, the rack scale architecture. If you think about how data centers are built today, there's lots of 1U, 2U boxes. Some people use blades. Some people use giant systems. But if you think about that, each of those are basically a fixed amount of gear. And just like an application developer, is requesting or getting guidance on what they should consume for their virtual machine, their container, we believe that the hardware should be composable too. So how do you right size? If you can basically take a CPU of one type, a certain amount of memory, and that should be able to change based off of the dynamics of what's happening in real time with your workload. So we're putting forward the rack scale architecture. I know there's a demo early system today. Early partners are getting access. And this will also have a strong API that let people basically monitor and control this at a very deep level. So in summary, what I want you to leave with is hyper-evolution is in effect. There's tons of things you can see here at IDF that focus in on a lot of the deep level technologies that we're bringing to bear. You saw that both Google and PayPal are doing some pretty impressive things to take their infrastructure to basically handle the demands of the connecting world. We're all optimizing. I hope you saw a pattern. We're trying to drive down TCO, increase performance. It's all about how the people connect in, and the data center's power to do that. We believe we should enable disaggregated decision making at scale. So when you're operating very large environments, you have concepts like watching and deciding actor patterns. And where are we heading? Are we going down the path of the Borg? I hope you all know the Borg is Singularity, Skynet, or maybe the Jetsons, right? But as the data centers in these systems start thinking for themselves, we're starting to do some pretty impressive stuff in the world. So, call to action. We really want software developers to be involved. This is how we're going to push this environment forward. So we do want you to join, take part in the data center software space. There's a number of open source projects that you can take part of. You heard OpenStack, you heard Mesos, you heard Kubernetes today. You can augment and extend on open standards and solutions. So this week, a thing called Redfish was launched, which is a new API, basically, REST API that theoretically will replace IPMI. There's plenty of open standards, open compute projects, but there's basically a way for software developers, hardware developers, all to get involved, get their hands on today, and help push us forward. And third point is join the conversations. So I think the whole data center environment and software is really opening up and pushing what we talk about. What I heard today was a lot of similar patterns. People are starting to solve problems, different levels of scale, different business issues, but it's all about how do we lower our TCO, increase our performance, and do amazing things that all of us can consume.